Welcome to your first online science lesson. I hope you guys are all okay. In your last lesson in class, by now you should have gone up to the end of page 2, so you should know how to draw circuit diagram symbols. If you don't, the memo will be put onto Teams. We did do that with you last year, so that shouldn't be new work. Today we're going to compare series and parallel circuits. Now, some classes have already done that. It's okay if you have. If you haven't, then we're going to do it now. Okay, so those of you who have already done it, it's just a little bit of revision for you. So we're going to start working on page 3. I did say before you start playing this video, you need to download the online FET circuit simulator. So to do that, you Google Colorado FET circuit simulator. Click on this link that goes to fet.colorado.edu. And then you're going to click on download. Once it's downloaded, you open it. Then you're going to click on lab. Double click on lab. Okay, so what this is it allows you to build online electric circuits. So on page 3 in your notes, it says, in this type of circuit, for series circuits, all the current flows through the whole circuit. So with a series circuit, there's no branches, there's no splitting. All the electricity, all the current goes through only one loop, does not split anyway. So the circuit that you see for series, let's build that. We're going to build the circuit in the same way that it is in your notes. On the cells that are in the online FET simulator, the left-hand side of this cell is a goldy color, the shorter side. It is actually the positive terminal of the cell, whereas the other side with the longer black side, that is the negative terminal of the cell. So in your notes, you can see how it matches up exactly with what's in your notes. Okay. Remember the longer, thinner line for your circuit symbol, that represents the positive terminal of the cell. That represents the positive terminal of the cell, whereas the shorter, fatter line, this line over here, that represents the negative terminal. So there's the positive terminal, and this side's a positive, the long thin line, the short fat line is the negative. Positive and negative. Okay. So in the circuit, we've got just one cell. So let's add just one cell. So you click from here and drag it across into your circuit. Okay. Then on either side of the cell, we've got some conducting wire. So it can drag some conducting wire. Remember, it must touch. If there's a gap like over here, then no current will flow through your circuit. You'll have an open circuit. All right, so I've got some conducting wire on either side. Then the circuit goes down. Let's make that a bit bigger. That goes down. And another piece of conducting wire. So you click, hold, and drag it down until where you want it to be. Then we've got some conducting wire going to the right. And then we've got a light bulb. So you're going to click and hold, drag a light bulb into your circuit. Okay. And another piece of conducting wire. So remember, current goes into the light bulb, through the light bulb filament, and across. You can see that no current is actually moving through the circuit right now, and that's because I haven't joined it up yet. But if I connect these two, then the light bulb is on. You can see that these yellow lines coming out mean that the light bulb is on. We've got current moving around the circuit. Notice how inside this blue circle, that represents one electron. See how there's a negative charge to show that it's a negative electron. Now, if this is the negative terminal of the battery, and I put a negative electron there, you should understand that like charges repel. So a negative electron would be repelled from the right-hand side of the battery, from the negative terminal of the battery, and go around the circuit, and a negative electron would be attracted to the positive terminal of the cell. And that's what electrons actually do, and current is the flow of moving charges, electrons. Remember, we told you that a conventional current is what we used to think happened, okay? and that would show the movement of a positive charge. So if over here I click on conventional, now I've got red arrows. The red represents a positive proton. If I put a positive proton near the positive terminal of the cell, it would be repelled. Like charges repel. Positive and positive would repel. So a conventional current would go from positive to negative around your circuit. And when I get here to the negative terminal, the positive proton would be attracted to that negative terminal. Okay. Now just to show you what you can do in the circuit, I'm going to not show any current for now. Actually, why not? Let's have some electrons going around. Okay. If I click on show values, it will show me the resistance of the light bulb. If you click on the light bulb, you can use the slider to adjust the resistance to whatever you want. So let's have a very low resistance, 1.5 ohms. Remember, resistance is measured in ohms. These lines are now so long because it shows that the light bulb is really bright because we've turned the resistance down. If resistance goes down, current is going to go up. Less resistance, more current. If I change the resistance of this light bulb and I make it go from, let's say, 1.5 up until 10 ohms, you can see how the lines from the light bulb showing that it's on are shorter, so that means that the light bulb is more dim than it was before. Remember, low resistance, more current, low resistance, more current, and so those lines are longer, which means that the bulb is brighter. So as I'm increasing the resistance, the lines are getting shorter, meaning that the bulb becomes more and more dim. Notice also how the electrons are moving around the circuit fairly slowly when we've got a resistance of 10 ohms. When I decrease the resistance of the light bulb, they move around a little bit faster. So low resistance, more current. Because there's more current, it means in order to get more current, the current has to move around the circuit a bit faster. Okay, so that's how you can adjust the resistance of a light bulb. If I were to add in a resistor into the circuit and join it up with some conducting wire, the resistors work the same way. Remember, a light bulb is a resistor. So if I click on this resistor, I can adjust the resistance of it using the slider. Okay. If you want to, you can also incorporate an ammeter into any part of your circuit. So to do that, drag an ammeter from there, like that, add in another piece of conducting wire to close your circuit, and this shows that we've got a current of 0.58 amps. Okay, I'm going to take out the light bulb, I'm going to take out the resistor, because in your notes, we don't have a resistor, we've got two light bulbs, even though light bulbs are resistors. Okay, so click on the rubbish bin to delete it. Let's put in another light bulb. Notice how they're both set to 10 amps. Notice how they're both set to 10 ohms. That one's 10 ohms, this one's 10 ohms. Okay, when I put in another bulb, did you see how the current slows down? It moves around the circuit more slowly. If you want, you can also check what the potential difference would be. If I take the negative side of this voltmeter and put it by the positive side of the battery, which is the wrong way to do it, but I am connecting the voltmeter in parallel, I get a negative value, negative 9 volts. The reason why is because I've connected it the wrong way around. If I put the negative side of the voltmeter onto the negative side of the battery and the positive side of the voltmeter on the positive side of the battery, then I'll get positive 9 volts. Now I want you to have a look and see what happens if you put the voltmeter across this light bulb, 4.5 volts and 4.5 volts. So we're going to talk about the importance of that in the next video. For now though, I just wanted you to see how to use this app, to see how to add in voltmeters, ammeters. If you want, you can add in an ammeter that you can move around. So if I put it over there, the target over there, it'll tell me that the current on this part of the circuit is 0.45 amps. That is 0.45 amps, there it's 0.45 amps, there it's 0.45 amps, there it's 0.45 amps. So we can say that the same current flows through any part of a series circuit, or in a series circuit, current is the same. Because wherever you are in the series circuit, the current's going to be 0.45 amps. So in your notes, current's only got one path to follow. the reading on ammeter 1, if I put an ammeter here where this one is ammeter A1, would equal to ammeter A2. If I put an ammeter over here at the top of the circuit, or over there, or over there, or over there, they would all read the same reading. So let's check. When the ammeter is in that position at 0.45, 0.45 amps, 0.45 amps, 0.45 amps. Between the light bulbs at 0.45 amps, after this light bulb at 0.45, 0.45, and 0.45. So please don't think that current goes around the circuit. Some current is used up by this bulb and less goes out of the bulb than what came in. Current at all points of the series circuit is the same. So that's very important. Same current flows through each resistor. You can make a little note over here. Where I was hoping to be able to type. I'm not sure that I can though. So you're going to write current in all parts of a series circuit is the same. Okay, so that's what you're going to write. Current at all parts of a series circuit is the same. Okay, I'm going to end this video, and then video 2 we're going to talk about how current splits in a parallel circuit.